Group delay constant. So we analyzed the things with the help of two people, Toji and Topi. That was group delay and phase delay. And we have seen that the group delay is constant for this category of people. Okay, Toji or the group delay constant. That's why they are able to achieve this. That means if a group of frequencies are passed through, each and every component, each and every frequency component will be delayed by the same amount. That's why we are able to recreate the shape of the input signal. We have seen this example with the help of a square wave, which was split into different sine frequency components and was passed with equal delay. And at the output, we were able to add all the sine waves and reconstruct the square wave perfectly back. So that happened because of constant group delay. All the frequency components should be delayed by same amount. That is the important fact. So Toji is very important for us, and Toji should be constant. And we have seen two cases where Toji is constant. First case was Toji is constant and Topi is also constant. Group delay, phase delay constant case. And we had another case where group delay is constant and we are able to preserve the shape, but the phase delay was not constant. Topi is not a constant. So we had two cases like this. I would like to classify like this. Design methods. This is an important observation. Very fundamental. Toji constant anyway because we are dealing with linear phase. That's capability, right? And Topi is constant and Topi not constant. And the case had to divide. So when Toji and Topi is constant, there is an important observation. Your impulse response, HFN, is symmetrical. Is symmetric. And symmetric about, you can say like this. The point of symmetry is referred as alpha, that is equal to n minus 1 by 2. That means if you have HFN has HFN the length is equal to n. HFN the length is n. At n minus 1 by 2, this will be symmetrical. I will show you an example. See, this is the example for case 1. Call it as case 1 and case 2. So case 1, I will show you an example. HFN signal at just okay. See, this is your n and this is your HFN. See, so this element is h of 0, let it be 1. Then h of 1, let it be 2. And this is second element. Let it be 3. Now this is third element, fourth element. Then definitely the impulse response will be like this. See, what is the length over here? What is the length? 0, 1, 2, 3, 4. You have 5 elements, right? So capital N is equal to 5. So what is n minus 1 by 2? 5 minus 1, 4 by 2. That will be 2. So about this particular point 2, you will have a symmetrical nature. This is the point of symmetry. This is h of 1 is equal to h of 3. H of 0 is equal to h of 4. So definitely the impulse response will be symmetric. In h of n, it will look like this. Either this is the case of an odd signal, or even signal the center point or symmetric. That has to be analyzed in detail. But in your UG level, this is enough. Observation. We will look at this. What will happen with this? H of n equal to, in this example, you can write, say 1, 2, 3, 2, 1. So this is symmetric about this particular point. This is symmetric. So that is one important observation. Second thing, when Toji is constant, group delay constant, he is able to preserve the shape. But phase delay is not constant. Phase delay constant. Then what happens is, your H of n is anti-symmetric. Anti-symmetric about alpha equal to, say, n minus 1 by 2. So we will see an example for that. Example for case 2. consider a signal like this, where this is n and h of n. See, anti-symmetric this should be 0, right? H of n should be equal to minus h of minus n varana. So center of symmetry idanu edukana. So if this is 1 and if this is 2, this is 1 and this is 2, what will be this particular two samples? Either minus 2 airikum, and this will be minus 1. This is minus 1 and this is minus 2. So this is what you mean by anti-symmetry. So your h of n can be written like this. H of n equal to, say, 1, 2, 0, minus 2, minus 1. Got it. This is an important observation. Note it. Then we will look into the design methods. Give you 1 minute to look into this. When group delay and phase delay are constant, your impulse response will be symmetrical about center of symmetry. And when group delay is constant and phase delay is not constant, your impulse response h of n is anti-symmetric. Same nature you will have with the spectrum also. We will see that. Okay. Can I proceed? Hello?
Yes, sir. Yes, sir.
Okay. So design methods, conclude. We will look into that once again. We have basically a FIR filter. You can make a heading, design methods. Just conclude design methods. Design methods. We will start with Fourier series method. Fourier series method. Direct windowing method. Both are same. We will look at that. Then we will have windowing method. Windowing method. This windowing method, we will use rectangular window, Hamming window, and Hanning window. Actually, the rectangular window you see now the Fourier series method. So I'm just skipping that. I'm calling it as Fourier series method separately. Windowing we will do using Hamming window and Hanning window. H-A-N-N-I-N-G, Hanning. This is H-A-M-M-I-N-G, Hamming window. And the last one is frequency sampling method. Frequency sampling method. So we'll discuss these three methods. And in the class windowing method and frequency sampling method. Windowing can be done using rectangular window, Hamming window, and Hanning window. Rectangular window you see in the same method and Fourier series method. Okay, both are same. Difference again than this topic time cover. This is pretty easy, very simple. This is also simple, but okay. There are some important points to be discussed. So we will start with Fourier series method. So you make the first subheading Fourier series method. So make the first subheading Fourier series method. And the basic theory and the method, then we will look into this. One problem is that this section recollect support. Okay. So the thing is that customer will give you a transfer function. See this, or not transfer function. He will give you a frequency response. Okay, what the customer is going to give you is a frequency response. Say something like this: h of e power j omega. Okay. So I would like to call it as HD. In all terms, I'm calling it as HD of e power j omega. So the frequency response will be like this. Say it is like this. Say up to this is 0 and this is pi. Normalize 0 to pi. So what filter is this? This is filter. This is minus pi to pi response. What kind of filter is this? Low pass, high pass, band stop. What kind of filter is this?
Band pass.
Band pass at shape right? But this is actually double-sided spectrum. Okay. The minus pi to pi plot it's double-sided spectrum. This is negative frequency component. So this is focus on the positive frequency component, that is from 0 to pi. Okay, always look at 0 to pi and say the type of filter. So what is this?
Low pass.
So this is a low pass filter, say with the cutoff frequency pi by 2. Pi by 2 on cutoff frequency. So this is a low pass filter. Customer, are you able to realize this exactly like this? It's an ideal filter, right? There is no transition band. This is the pass band and this is the stop band. It's ideal. Perfectly cutoff frequency is referred as pi by 2. Customer will have that particular knowledge only. So you will be asked to design this desired. This is his desire. Customer desire. So this is the desired say frequency response. So the question will start like this. Frequency response will be given to you. Then you may be asked to design a filter. Filter design, you have to find h of n. H of n you will have some coefficients like 1, 2, 3, 4, something like that. That's a filter coefficient here. Okay, repeat. Okay, so this is the desired response. So this is available with me. HD, capital H, frequency response is available with me. I want this thing. I want the time domain. So what is the easiest method? You transform your frequency domain to time domain. You take the inverse for your series. Inverse edukka. Okay, that means you find h of n. Let me call it as h of n. H of n equal to, you have to use the inverse Fourier series equation. That is 1 pi 2 pi into integral minus pi to pi hd of e power j omega into e raised to plus j omega. Series frequency minus j omega. Here it will be plus j omega and d omega. So when it is a continuous plot, integration symbol uses. So this is how we can transform it into frequency. H of n very easy to obtain the equation. Got it? So the main problem with this h of n will be, do remember, h of n this will have infinite number of terms. H of n is limit. It will have infinite number of terms. Your impulse response will have infinite number of terms. What you are asked to design? An FIR filter, finite impulse response filter. That means you have to cut short this infinite terms to some finite number of terms. Say that will be addressed by capital N. Say capital N equal to 11. That means you have to cut short your total impulse response to 11 terms, say from minus 5 to 5, something like this. Now, h of minus 5 to minus plus 5, you will have 5 minus 5 0, then up to 5, you will have 11 terms, right? Including 0, you will have 11 terms. This term. Sometimes you may ask it to restrict to say 15 terms. Then it should vary from minus 7 to 7. Index should vary from minus 7 to 7. H of minus 7 to h of 7. You have to compute this if you are asked for n equal to 50. So the important thing is you have to cut short this. So this is having infinite number of terms. So this is not my answer. This is the answer. So I am not ready to call it as h of n. H of n is the final answer. HD of n. I am calling it as HD of n. Because this is the time domain corresponding to this desired frequency domain. If you are able to save this infinite terms, you will get exactly the ideal filter. Ideal filter infinite time in story that. But I am not able to store that because then I have to cut short it. Cut short. Cut short means cut short I will like to call it as h dash of n h dash of n h dash of n. Okay, so h dash of n will be you can say it's called a truncation. Truncation. Cut short ചെയ്യുന്നതിനെ നമ്മൾ വിളിക്കുന്ന പേരാണ് truncation. So this is the truncated version of h of n. H of n in the truncated version or hd of n. So this is you can write it as hd of n, exactly hd of n, when you can say like this, how can you address this when n equal to 11 minus 5 to 5 എങ്ങനെ address ചെയ്യാം? You can call it as n minus 1 by 2. ശരിയല്ലേ? n odd ആയിട്ടുള്ള പ്രോബ്ലം മാത്രമേ നമ്മൾ ചെയ്യുള്ളൂ. Okay, n minus 1 by 2, you can say minus of this less than or equal to n less than or equal to n minus 1 by 2. അല്ലെങ്കിൽ ഒരു മോഡുലസ് സിംബൽ ഇട്ടങ്ങ് എഴുതിയാലും മതി. Okay, this is pretty more clear. Else this its value will be 0. For all other values of n, its value will be 0. This is called a truncation. നമുക്ക് ഒരു എക്സാമ്പിൾ ചെയ്യുമ്പോഴേ കാര്യങ്ങൾ കുറെ കൂടി ക്ലിയർ ആവുള്ളൂ. തൽക്കാലം ഇത്ര മനസ്സിലാക്കുക. Here you have infinite terms. Here you have truncated to how many terms? Truncation to n terms, n number of terms. Truncation to n number of terms. So that is called h dash of n. Now another problem with this is it is not realizable. ഇതിന് ഒരു നെഗറ്റീവ് സൈഡും വരും. h of n ന് ഒരു നെഗറ്റീവ് സൈഡും വരും. സോറി, h dash of n ന് ഒരു നെഗറ്റീവ് സൈഡും വരും. -5 to 5, -7 to 7. ആക്ച്വലി ഇത് റിയലൈസബിൾ അല്ല. ഇറ്റ് ഈസ് എ നോൺ കോസൽ സിഗ്നൽ. നമുക്ക് ഇതിനെ കോസൽ ആക്കണമെങ്കിൽ എന്ത് ചെയ്യുക? കംപ്ലീറ്റ്ലി റൈറ്റ് സൈഡ് ആക്കുക അല്ലെ? കോസൽ എന്ന് പറയുന്നത് എന്താണ്? കംപ്ലീറ്റ്ലി പോസിറ്റീവ് വാല്യൂസിലേക്ക് മാറാം. സോ ഇൻസ്റ്റെഡ് ഓഫ് -5 to 5, ഇനി നമുക്ക് എങ്ങോട്ട് മാറണം? 0 to 10 ആയിട്ട് വരും. -7 to 7 ആണെങ്കിൽ അതിന് എന്ത് ചെയ്യുക? 0 to 15 ആക്കുക. സോ വാട്ട് യു ഹാവ് ടു ഡു? യു ഹാവ് ടു റൈറ്റ് ഷിഫ്റ്റ് ദ സിഗ്നൽ ബൈ n minus 1 by 2 unit. n minus 1 by 2 units റൈറ്റ് ഷിഫ്റ്റ് ചെയ്താൽ മതി സിഗ്നലിന്. നമുക്കത് നോക്കാം. That will be your final answer. h of n. This is making the signal causal എന്ന് വേണമെങ്കിൽ എഴുതാം. Making it causal. Making your h of n. Making your h of n causal. So okay, that is your final h of n. ഇതിനെ ഞാൻ h of n എന്ന് വിളിക്കുന്നത്. കണ്ടോ, ഇവിടെ h dash എന്നാണ് വിളിച്ചത്. So what is your h of n now? h of n is equal to h dash of n minus n minus 1 by 2. Just ഇതിനെ ഒരു n minus 1 by 2 units shift ചെയ്യുക. That's it. And this will be my final designed filter. So, we have 3 കാര്യങ്ങൾ ചെയ്തു. 1, 2, 3. First is inverse Fourier series. Second is truncation. Third is making the impulse response causal. Adine causal aaka. Or you can say that it's a perfectly realizable filter. But a filter realizable alla. But a filter realizable alla. കുറച്ച് കാര്യങ്ങളൊക്കെ ഒന്ന് പിടിയിട്ട് കാണും. ഒരു പ്രോബ്ലം ചെയ്തിട്ട് we will come back. Okay, we will see this in detail. So you write one question. You write the first question. ഇത് വിഷമിക്കേണ്ട, ഇത് നമുക്ക് ഇപ്പൊ നോക്കാം. Okay, we'll look into this. So write the first question. Let me see one. Design an FIR filter with n equal to capital 11. Design an FIR filter with n is equal to capital 11 for the given magnitude response. For the given magnitude response. For the given magnitude response. So a magnitude response is provided by the customer. Customer has given you a magnitude response. He don't know anything else. This is omega, and this is say h of e power j omega. Sometimes customer will call it as h of e power j omega, but you have to name it as hd of e power j omega. Okay, the question h of e power j omega in thannalim you just call it as hd, because for us when you are a designer, it's your right to modify that. So the filter is, or the response is given like this. This is the given response. So what is the customer requirement? You have to design an FIR filter. Say, what kind of filter is this? What type of filter is this?
Low pass filter.
With cutoff frequency?
5/2.
അങ്ങനെ simple ആയിട്ട് വേണമെങ്കിൽ customer പറയാം. I need a low pass filter with cutoff frequency 5/2. Okay. So let's start the design. What is the first step? What is the first step? Remember this.
HD of n.
HD of n. You take the inverse Fourier series. Okay, so help me to find HD of n. HD of n. 1 by 2 pi into integral. I will write the equation once. ഞാൻ ഇതിനൊരു ഷോർട്ട് കട്ട് പറയാം. തൽക്കാലം നമ്മൾ പ്രോബ്ലം ചെയ്യുക കേട്ടോ. നിങ്ങൾ ഒന്ന് രണ്ടെണ്ണം ചെയ്യുക. ഇന്റഗ്രേഷൻ ഒക്കെ ബുദ്ധിമുട്ടുള്ളവർക്ക് ഞാൻ ഒരു ഈസി മെത്തേഡ് പറഞ്ഞുതരാം. So this was the equation e raised to plus j omega n d omega, right? So this is equal to 1 by 2 pi, and according to my response, just a minute, you just try to do that, integrate it. So you just integrate it. Your frequency response, is it audible?
Yes, sir.
Okay, minus pi by 2 to pi by 2. That is the signal limit. Else the signal is 0. So I am restricting it to minus pi by 2 to pi by 2. At this time, your HDF e power j omega, that is 1. Actually, this is the magnitude plot. You want the magnitude of it. Okay. So that is 1 into e raised to j omega n d omega. Now integrate it. 1 by 2 pi into integral of e raised to j omega n. Integral of e raised to j omega n is e raised to j omega n itself with respect to omega. So by jn is will be added. Integration limit is minus pi by 2 to pi by 2. Just apply the limits. Jn is in the common. I will write over here for the visibility. 2 pi jn and then into e raised to j omega. J omega can be replaced with pi by 2. J pi by 2n minus e raised to minus j pi by 2 n. So what is this thing? By pi n വെളിയിലിടുകയാണ്. 2j എന്ന് പറയുന്നതിനെ കട്ട് ചെയ്ത് അകത്തേക്ക് എഴുതുകയാണ്. So you will have 1 by pi n into what is this thing?
Sin pi by 2.
Sin pi by 2. Sin pi by 2 n. So that's it. That is the final answer. E raised sin theta is equal to e raised to j theta minus e raised to minus j theta by 2j. Okay, that's sin theta എന്നുള്ള equation. So this is very simple. HD of n is this thing. ഇതാണ് നിങ്ങളുടെ impulse response. If you are able to store this, that means n varies from say all values of n up to infinity is acceptable. Okay, അങ്ങനെ നിങ്ങൾക്ക് സ്റ്റോർ ചെയ്യാൻ പറ്റുമെങ്കിൽ exactly you will get the same response. That is ideal. But you have to cut short it to make it an FIR filter with 11. Say capital N is equal to 11. You have to cut short it. So this is the first step. What is your HD of n? I will write it. Running out of time. You got the HD of n as sin pi by 2n divided by pi n. Now tell me what is the second step? Truncation. Truncation to say n equal to 11. N equal to 11 are truncate. That can be called as h dash of n. That is h dash of n. So h dash of n equal to sin pi by 2n. Step just when for minus 5 to 5. Or minus 5 less than or equal to n less than or equal to 5, we can say this. That means you have to find h dash of 0, then you have to find h dash of minus 5 to 5 ആണ് ചെയ്യുന്നത് അല്ലേ. So h dash of minus 1, that will be equal to h dash of 1. ഇത് രണ്ട് ഈക്വൽ ആയിരിക്കും. സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് നോക്കുമ്പോൾ തന്നെ അറിയാം, അല്ലെങ്കിലും ഡയറക്റ്റ് പറയാൻ പറ്റും. സിമെട്രിക്കൽ ഇമ്പൾസ് റെസ്പോൺസ് ആണ്. The impulse response will be symmetrical. H dash of minus 2 will be equal to h dash of 2. Then h dash of minus 3 will be equal to h dash of 3. Then h dash of minus 4 will be equal to h dash of 4. Then h dash of minus 5 will be equal to h dash of 5. This is how you have to find all the 11 values. Ready? Now let's find h dash of 0. H dash of 0, ഞാൻ ഇവിടെ calculation കാണിക്കാം. H dash of 0. ഇത് പ്രത്യേകം ശ്രദ്ധിക്കണം. ഇവിടെ 0/0 ഫോം വരും. സി സൈൻ π/2 n by pi n ആണ്. When you substitute n equal to 0, sin 0 is 0. 0/0 ഫോം വരും. So what you have to do? എന്ത് ചെയ്യാൻ പറ്റും? ലിമിറ്റ് അപ്ലൈ, ലിമിറ്റ് n tends to 0. ആദ്യത്തേന് ലിമിറ്റ് അപ്ലൈ ചെയ്യേണ്ടി വരും ഓൾവേസ്. So what is this thing? Limit n tends to 0. Sin π/2 n by, ഇവിടെ π/2 ആണെങ്കിൽ നിങ്ങൾക്ക് 1 എന്ന് വിളിക്കായിരുന്നു അല്ലേ? ശരിയല്ലേ? ലിമിറ്റ് ഇക്വേഷൻസ് ഓർത്തിരിക്കുക. സൈൻ തീറ്റ ബൈ തീറ്റ ഫോമിൽ വന്നാൽ യു ക്യാൻ റൈറ്റ് ഇറ്റ് ആസ് 1. ഇവിടെ തീറ്റ എന്ന് പറയുന്നത് π/2 എന്നാണ്. ഇവിടെ പൈ എന്നേ ഉള്ളൂ. സോ മേക്ക് ഇറ്റ് by 2 to cancel the effect, multiply with 2 in the denominator. So what is this term? This will be 1. So the answer is 1/2. അല്ലെങ്കിൽ ഇത് ചെയ്യാൻ ബുദ്ധിമുട്ടുള്ളവർ എൽ ഹോസ്പിറ്റൽ റൂളിലേക്ക് പോവാം. നമുക്ക് ടൈം ഇല്ല, അടുത്ത ദിവസം അടുത്ത പ്രോബ്ലം ചെയ്യുമ്പോൾ നമുക്ക് അങ്ങനെ നോക്കാം. ഓക്കെ, 1/2. So this is 1/2. Now find h dash of 1 and -1. 1 കണ്ടുപിടിച്ചാൽ മതി, both will be equal. h dash of 1 sin π/2 into 1, n ന്റെ വാല്യൂ 1 ആക്കി, divided by pi into 1, pi n, n ന്റെ വാല്യൂ 1 ആക്കി. So sin π/2 by π/2. Sin π/2 is how much? 1. This is 1/pi. Okay, you find the value of 1/pi. Pi the value substitute here, that will be 0.3183. 0.3183. അടുത്ത ഒരെണ്ണോടെ നിങ്ങളൊന്ന് കമ്പ്യൂട്ട് ചെയ്യൂ. ഫൈൻഡ്, നിങ്ങൾ -1 ചെയ്ത് നോക്കുക കേട്ടോ. -1 ഇട്ടാൽ എന്ത് സംഭവിക്കും? സൈൻ മൈനസ്, ഇവിടെ മൈനസ് വെളിയിൽ വരും, താഴെ മൈനസ് വരും, മൈനസ് വിൽ ബിക്കം പ്ലസ്. ഓക്കെ, ഇത് എപ്പോഴും സൈനിലേ വരുള്ളൂ, അതാണ് ഇതിന്റെ ഫാക്ട്. അത് എന്തുകൊണ്ടാണെന്ന് നമുക്ക് നോക്കാം. ഒന്ന് രണ്ട് പ്രോബ്ലം പ്രാക്ടീസ് ചെയ്തിട്ട് നോക്കാം. സോ ഫൈൻഡ് ദ റിമൈനിങ് വാല്യൂസ്. 2 എന്ന് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് നോക്കുക. h dash of 2 സൈൻ π/2 into n, n is 2, അപ്പൊ എളുപ്പമായി 0 ആയിപ്പോയി അല്ലെ, ഡിവൈഡഡ് ബൈ pi into n, റൈറ്റ്? സോ 2 will get cancelled. Sin pi is 0, visible ആണോ? Sin pi is 0, so this will be 0. So this is 0. Likewise, you have to find all the other terms. ഞാൻ അതൊന്ന് തൽക്കാലം ടൈം ഷോർട്ടേജ് ഉള്ളതുകൊണ്ട് ഒന്ന് കോപ്പി ചെയ്യാം. This is -0.106, -0.106. This is 0 and this is 0.06366. അടുത്ത ദിവസം നമുക്കൊരു ഫുൾ പ്രോബ്ലം എല്ലാം സോൾവ് ചെയ്ത് തന്നെ നോക്കാം. ഓക്കെ, so this is called a truncation. എളുപ്പമല്ലേ? We will wind up the problem with last step. Last step എന്ന് പറയുന്നത് എന്താണ്? What is the problem with this transfer function or this impulse response?
Non-causal.
Non-causal. It has got the negative side also. It is not realizable. It is non-causal and it is not realizable. So make it a practical filter. You have to right shift it by 5 units. ഇപ്പൊ -5 to 5 ആണുള്ളത്. അപ്പൊ എത്ര യൂണിറ്റ്സ് ഷിഫ്റ്റ് ചെയ്യണം? 5 units. So to make it causal, you have to right shift it by n-1/2 units, which implies 5 units. 5 units right shift ചെയ്യുക. വെരി സിമ്പിൾ. അതിനൊരു മെത്തേഡ് ഞാൻ പറഞ്ഞുതരാം. മെത്തേഡ് എന്ന് പറയാനൊന്നുമില്ല, ഈസി ആയിട്ട് ചെയ്യാൻ വേണ്ടി, തെറ്റിപ്പോയി ചെയ്യാൻ വേണ്ടി എന്ത് ചെയ്യുക, ഇതിന്റെ കൂടെ എല്ലാ ഇൻഡെക്സ് അങ്ങ് 5 ആഡ് ചെയ്താൽ പോരെ. ജസ്റ്റ് ആഡ് ദ ഇൻഡെക്സ് ബൈ 5. Just add the index by 5. So h dash of 0 ക്ക് പകരം you can write it as h of, ഞാൻ ക്ലാസ്സിൽ ചെയ്യുകയാണെങ്കിൽ ബോർഡിൽ ഇതിനെല്ലാം മായ്ക്കും. h dash മാറ്റിയിട്ടെല്ലാം h ആക്കും, ഇൻഡെക്സ് മാറ്റിയിട്ട് ജസ്റ്റ് +5 വേർഷൻ എഴുതും. That's what I am doing over here. So h of 5 is 1/2. മനസ്സിലാകുന്നുണ്ടോ? h of 5 is 1/2. Then next h of -1 + 5 4 ആവും അല്ലേ, equal to h of h dash മാറ്റി ഇപ്പൊ h ആക്കി. ഓക്കെ, 1 + 5, that will be 6. That will be equal to 0.3183. Next ഒന്നുകൂടെ നോക്കാം. h of -2, h dash of -2 മാറ്റിയിട്ട് h of -2 + 5, this will be 3. That will be equal to h of 2 + 5, that will be 7. That will be 0. Next h of പറഞ്ഞു
8.
h 8 അല്ല, -3. 2. Okay, that will be equal to h of 8. That will be 0. Next, h of 1 will be equal to h of 9. That will be equal to, sorry, the 0 minus 0.106. This will be 0. Then next, h of 0 will be equal to h of 10. That will be equal to 0.06366. And this will be your final answer. So let me write the impulse response. Your design complete on the h of n on the okay, h of 0 no 0.06366. Next, then h of 0, first index. H of 1 and 0. H of 2 and h of 2 and minus 0.106. H of 3 is 0. H of 4 is 0.3183. That will be the next. H of 5. H of 5 is 1 by 2. This is the point of symmetry. Next, h of 6 h of 6. 0.3183. Next, h of 7. 0. H of 8 minus 0.106. H of 9. 0. H of 10. Last element. 0.06366. So that will be the final answer. Here you can see that this is the point of symmetry. These 2 points are equal. Now this green color mark. Okay. Next, these 2 points are equal. Right? These 2 are equal. This is equal to the last. So this is symmetrical filter response we have obtained. So this is your designed filter. Let me conclude with one point. We'll stop right now. Near filter design implement. How will you practically do this? When you have a signal say x of n. This is your filter h of n. How will you find the output y of n?
Direct for realization.
Okay, realization. Right. If h of n impulse response directly mathematically, which operator can be used?
Convolution.
Convolution. Just perform convolution. Just a convolution perform. Isn't it? You will get the result. So I would like to conclude the thing. We will see the 2 or 3 problems more. Okay. For one or minimum Fourier series method, this is the desired response. First step is you take the inverse Fourier series, you will get this impulse response. What is the problem with this HD of n? HD of n is the problem. Why this is not my answer? What is the problem with this? It has infinite number of terms. So you go for truncation. You truncate it like this. Now, what is the problem with this truncated h of n? I call it as it is non-causal. It is not realizable. It has a negative part also. So you shift it to you make it causal, shifting it to right, so that your signal will become completely realizable. And that is the final solution. That is your design filter. So clear ആയവർക്ക് leave ചെയ്യാം, അല്ലാത്തവർ wait ചെയ്യാം. ഞാൻ doubts ഉണ്ടെങ്കിൽ clear